Thank you guys for attending today and welcome um, to the AI Talk series. We are very happy to have Sherin Thomas today from Grid.ai to talk about MLOps in production. Before that, I'll just quickly give you a short overview of what OffNote Labs is, and then we'll start. Thank you very much. Yeah. So OffNote Labs is a home for independent researchers and builders, and our goal is to help young researchers grow and shine via the mentorship of senior researchers. So the idea is to be an open platform for doing research without boundaries. There's no kidding and no PhD involved here. The basis of our OffNote Labs is the observation that for the first time in computing history, there is this democratization of knowledge and research at this scale, especially in the field of AI, and that has led to a rapid increase in the number of eager and young learners, and who are self-driven and can dig deep into various topics, read papers, and dig deep into code, and without external help, without mentors, they're only able to get to a particular level, and unless they go into the master's and PhD program. But master and PhD is a long-term commitment, and they may not be sure, they may not want to be to do that. So OffNote Labs is a platform to help them have mentors, help them do research and dig into cutting edge research. So we are looking for young researchers who are eager to learn and do research and become experts in what they do, and do the particular characteristic they're looking for is that they are self-driven and they're able to push beyond their comfort zones. And we're also looking for mentors who want to pursue research without any environmental constraints and on problems they're passionate about, and share their journey and learnings with young researchers. So that's quick intro to OffNote Labs. Our website is offnote.co. You can follow us on LinkedIn and Medium and read about the experience of previous young researchers on Medium, and feel free to ping us and to learn more. Okay, so that said, I will pass on the mic to Sherin, and we're very happy that he has agreed to give us a talk. MLOps is one of the one of the hottest and least one of the hottest topic that everybody wants to learn about, and it's a broad spectrum. There are several components to it, and Sherin is going to give a broad overview of the whole domain or paradigm. And so again, feel free to ask questions. There's a chat box where you can just type in your questions, and if you want to ask in person, you talk and ask. There's a raised hand icon. You can click on that, and I'll give you the mic. So again, thanks, Sherin. I'll switch off my sharing so that you can. Good.
All right. Thank you so much, Nishant. Thanks everyone for having me here. So yeah, I'll first try to share my screen and then. Can you guys see the screen? Hello?
Yes, now I can see that.
Okay, perfect.
Yeah.
Right. Okay, so I think I can see. Oh, perfect. Okay, I can see the chat. So the way I wanted to take this is, make this as interactive as possible. So like Nishant said, I'm covering a 1,000 feet overview of what MLOps in production look like. This all comes from my experience in the last few years building some of the MLOps tool. tools. So I would be more than happy to jump into the concepts or more details if you want to talk about those. So feel free to stop me, send a message in this chat, or raise a hand. Then we can take it from there. You don't have to wait for end of the presentation to ask questions.
Yeah. So just to quickly, I'll be monitoring the chat and I'll periodically pause so that I can and then
Okay.
questions to you.
Okay, sounds great. Okay, well, so a quick introduction about me. As Nishant said, I'm a software engineer at Grid.ai right now. I am still part of RedisAI's core development team. But previously, the journey is I started as a software engineer who works on security stuff in SLK software service. Like when I started, I was, I wanted to be a hacker, right? And then once I started job, after 6 months, I realized, the job is not as fun as you see in movies. So, I moved from that domain and become a typical software engineer. And then this is even before the hype of deep learning started, right? So this is when people were using Torch, the Torch or Theano for deep learning research. Deep learning was not at production, streamlined to production yet. Then I moved to deep learning and deep learning Bangalore. The organization was one of the key component in the journey, and that's how I met Nishant. From there, I moved to CoWorks, and then that's where I started building some of the AI stuff. Then I moved to Tensorflow because Tensorflow was building some of the core component of this MLOps system, and then to Grid.ai. So this is my journey. I'm at it second everywhere, LinkedIn, Twitter, everywhere. So if you want to talk to me, even after the presentation, if you want to discuss about MLOps or the things that I do, or questions or the things that, I don't know, which is a lot in MLOps itself. So yeah, feel free to reach out and then we can continue from there. Okay, so like I said, the whole conversation is built around, the whole presentation is built around why MLOps. Because this is one of the questions that I used to face a lot, right? Especially people who run things by themselves, like researchers or small companies. They could do things by themselves. So it's at that stage, it's probably difficult to find the reason of the existence of this stream. Why? So that's the whole conversation is built around. So I introduce the components in a production-ready ML system first. Then we go to each of these components and try to address the problems existing in each of this component. And then that's how I want to move. Also, like I said, feel free to jump in if you have faced some issues that I haven't addressed here. We can talk about that as well. So the way I see MLOps, it's probably not a generalized view. Everyone look at MLOps. The way I see it is, there was the software 1.0, the left-hand side that you see, source code, compiler, executable, VM, these things, the test cases. The software 1.0 stack had something for ops, right? We call it DevOps, then that became GitOps, different terminologies. When we move to data-defined software or software 2.0, there is an analogous component to everyone on the left-hand side. And managing the ops in the software 2.0 stack wasn't really exactly same as software 1.0 stack. It's essentially because the whole process in the software 2.0 stack is different compared to software 1.0 stack. So it's not only that, the software 2.0 stack consists of components in the software 1.0 as well, right? You still have source code, you still have test cases, you still have compiler, etc. So MLOps, the way I look at it is, MLOps is this big umbrella that handles the ops of software 1.0 and 2.0. So obviously that brings a lot of challenges, right? Because the major key player in the software 2.0 stack is the data scientist or the researchers, as we call them. So it's almost always, it's very likely that data scientists or the researchers, they are hardcore in their domain of expertise. It's unreasonable to expect them to be, hardcore DevOps guys as well. So the data scientists should be focusing on the hardcore problem, while engineers should be able to give them the solution to handle the ops problem that they would be facing. So this is a challenge. Right now, even though the ecosystem is maturing, right now the tool set that brings together this ops platform is not mature enough to give this option to data scientists. It's still a leaky abstraction, right? Data scientists still need to understand some part of the ops unless they have a ops team or an engineering team. Another major problem that I see in the industry is data scientists build something in 3 weeks or 4 weeks time, let's say, and the time that it takes to move that component, that model from the data scientist system to production, that probably take another 9 months. By that time, the data might have changed, the distribution might have changed, your model is not really good anymore, right? As Chip said in all of the presentation, the data changes, and I mean the expectation of model once it's built, it's the accuracy, the performance stays same. It's a myth, right? So it keeps on degrading as the data evolve. So there is an expense component to it, the expertise component to it. The third component is tooling. There is no standards. Different people, different companies come up with their own standard, and there is no standardized way of looking at the tools. So, I mean, if you take the example of frameworks like TensorFlow or PyTorch, they are converging to one way of approaching things. Even though there are, slight variation, there is now a standard, at least the way people see it, like an eager mode where you can quickly prototype something, then move to production through a process of, scripting or converting that to more of a static graph. So I would say the framework world is converging, but the tool ecosystem is not. So some of the pieces in the MLOps tool ecosystem is not even mature enough. It's still under research, like active learning and stuff. The challenge continues. So the next problem is the shininess of AI is wearing off, right? You probably have read about different big companies laying off their big data teams, big AI team. And Fortune 500 companies reporting about the mistake that they have made with the AI team. They consider AI as a strategic advantage at some point in time, 3 years, 4 years ago. But through the experience, they realize it's it's too much of a cost, but the return is not really worth. It's return of investment. The ROI is not worth. So this people are realizing this. So the problem, as Josh Tobin, the previous UC Berkeley or the full stack deep learning guy, as he defines the problem, the people who realize the whole system as collecting or identifying the problem, collecting data, cleaning the data, training the model, testing, evaluating, and deploy. So they look at the machine learning spectrum, the pipeline as the component that starts from here and ends here, right? So Josh call it as flat Earth ML. So people who can't see beyond this, it's like the people who believed in flat Earth, right? So people who if they can't see what is after the horizon, they believe Earth is flat. It's the concept is same. But there is another component to it, right? There's a loop that after deploying to production, then you start analyzing your data, production performance, then that is looped back to the training system. So you collect data, retrain the model, redeploy. So there's a loop. So there's another whole spectrum to the productionizing deep learning stuff has. Right. So these are the non-technical challenges as I would like to introduce. Next, we will go to the components, of a deep learning system. I'm really sorry about my poor drawing skill. So I'm trying to convey, the message here. So feel free to ask questions if you have anything about this diagram. So I'll quickly explain what I try to depict here. The way I see it is the production ML system has majorly two components, right? The training, that as you see here, and then the serving. So this two pillars of the production system is connected together. And there is two parallel component that running throughout the whole system. One is monitoring. You monitor your data source, you monitor your training system, you monitor your serving system, you always monitor your artifact store. Then there is a hardware component to it. All of this requires the hardware piece to it. Now, starting with the flow, you identify the problem that happened, and then you have a source where you put your data. From source, you move the data to data store. So there would be a pipeline system that clean up the data, make sure the data in the proper format, and store that in the data store, which then goes to the training system. Then the training, once the training is done, you save the artifact, or as the training progresses, you save the artifact to artifact store. And the artifact store, once you are confident about your system, it gets deployed to the serving system through probably a CI/CD or a manual intervention, a manual trigger. From the serving system, you start collecting data, you analyze the data, you monitor the data, and you push that data back to your data store. And at some point, you decide you need to retrain the model. So there is that's another decision that you need to make, right? At what point we need to retrain the data, retrain the model. So this is the loop. Now, a CI/CD component which runs or which controls the whole thing, that's what I try to depict in the center. So there are other pieces to the whole machine learning system, but I like the problem statement, etc. I did not want to include that here. This is very specific to a production machine learning system, not really oriented to the resource side of it. Right. So, like I said, it has, in my view, there are two major pillars, training and serving. So the rest of the conversation, the rest of the presentation is going to focus on these two things separately. So first we will start with training, then we go to serving. And so what we are going to do is, like I said previously, we take each of this component and try to address the problem that exists, which MLOps could solve. So first we will start with training. So training is easy, right? Until it is not. So if you are training your model on a single GPU and a single machine, or if you have got
sorry, can I just interrupt? And are there any questions till this point? Please feel free to type in the chat or raise your hand. Any questions? Okay, sounds good. Yeah, again, we have a virtual community here, so please feel free to speak up, and it's a bit hard, but please do share your questions. Okay, Sherin, please continue.
Great. Okay, so I'll continue to the rest. So yeah, like I said, training is easy until it is not, right? So if you're training on a laptop or one machine, one GPU, you have a local DG station, or you're setting it up in AWS, it's easy. But it's hard when you try to scale up. It's hard when you need to do retraining on the live data. It's hard when you want to monitor your stuff in real time and look at the metrics, not the ground truth metrics like accuracy or precision, etc., but the metrics where you have to figure out if things goes wrong. So when you introduce such complicated components to your training system, things are hard. It is difficult. So this is the same diagram from what we have seen before. So for training pillar, I think apart from the serving thing here, every piece of this MLOps of this production machine learning system is associated with training. So we start from the hardware and environment, right? What are the challenges that we face normally when it comes to the hardware and environment? So the problems that I depict here, which I felt are the most common problem, I would really encourage you to message here if you have seen some other issues that I haven't addressed here. So one of the biggest problem that I see when I talk to data scientists is different cloud providers has different way of doing things, obviously. And sometimes it's essential for moving from one to the other cloud providers because of the providings because of the way things have been arranged in one cloud providers, because of cost, different reasons. So understanding this nitty-gritties for a data scientist is difficult. Like AWS Ops itself is a job, or Azure Ops itself is a job. So having that knowledge in one person along with the machine learning expertise is difficult. Dependency management is another major problem, right? When it comes to dependency management, it's not just requirements.txt or conda environment YAML file, right? It's much more than that. For example, if you have a GraphViz in your package, that means your system needs GraphViz system package. Also, it's not just pip install GraphViz. You need the system package GraphViz also install your machine. Similar, another option is another example is OpenCV. Conda solves some of this really well, but not always. So there is another package, another example that I don't remember exactly. A pill or OpenCV headless, which is a pip installable package. But I guess when you pull that from source, you need to pass a flag to the compiler so that it builds in a certain way. So these are the problems that comes along with the dependency management, and dependency management is a hard problem. And engineers might not understand this. I did not understand this, but in my previous experience, there are a lot of data scientists or researchers who does not have a requirements.txt file or a dependency file. It's probably because they try to prototype through the problem and try to fix things and finding their way through really complicated issues that they're facing. It's a common. I don't say it's a common pattern, but you see this often. So figuring out the dependencies is an extremely hard problem. Analyzing the cost difference and efficient resource utilization. The picture that you see there, it's a Converge.io. It's an MLOps platform. The way they show the resource utilization. So they have a graph that says, on average, 40% of the resource are being wasted. If you're a small company, you probably cannot afford that waste. If you're a big company, that 40%, that account to a lot of money. But if you're a big company, you probably have a solution for that already. So efficient resource utilization is hard. We'll move on to the second component, which is distributed training, right? So why distributed training, or what MLOps could do or help in distributed training? So why distributed training is probably an obvious answer. You have hundreds of experiments that you would want to run, right? You are doing a hyperparameter sweep, you're trying to find the best experiment, and you try to kill experiments as it goes through and try to find that one experiment which doing really well. So hundreds of concurrent experiment management is difficult. It's probably not possible at all if you're doing a single machine. You want to distribute your setup, and again, even for a single experiment, you might need to use different machines, right? So you might different nodes or different GPUs. You might be sharing the batch across different nodes, like across different GPUs. So distribution happens in different levels, and distribution is hard. So packages like PyTorch Lightning try to solve this problem, right? So you can pass a number of nodes that you want. But even with that, there are other nitty-gritties that you would have to solve. Like you need to have that number of machines up. You need to go through each of those machines and set the master IP address, etc., so that they can communicate together. So systems like Horobo, Torch Elastic, etc., try to solve this in different ways. But I still think there is, there is an ops component to it that can eliminate a lot of things that a data science need to know before doing this concurrent, distributed training. So one solution that I have identified from my experience is it's not a solution, but it's one step closer. It would make yourself one step closer to the solution, is to containerize your application. Even if you're not distributing your stuff, it's better if you're containerizing your things so that you can put this into a cluster at some point in time later. That brings us to the next problem: orchestrating the infrastructure, right? So how will we be able to orchestrate the infrastructure? And obviously the solution that would come to your mind is Kubernetes. But again, Kubernetes is how hard it is to get started with Kubernetes. Two other major challenges is you might need to retrain the model continuously and frequently, right? The data changes, you look at the data, you see some distribution shift. You take the model, you take the new data, you retrain it, you push that retrained model to production. How often would you push this to production? Depends, right? So there was a statistic, I think, in one of the chips talk. Facebook pushes every 11 second. HC pushes 150 times per day. I don't exactly remember the numbers, but these are the types of the problem that you try to deal with. Another major problem is reproducibility, right? So you have hundreds of experiments. And let's say you deploy one of the model to production. Let's say a loan, whether a user is eligible for a loan or not. Let's say your model predicted that the user is not eligible. Now there is a question that user raised, why, right? You should be able to reproduce that exact system and explain and have the explainability component to it so that you are safe from a lot of legal complications. Any questions so far? So we have covered two components, the hardware and distributed training. Any questions so far? Okay, I trust there is none, so I'm going to move forward. Okay, the third piece, the data itself, right? So data is huge. Storage, versioning, and collaboration is hard. Then the file-based data store has inherent problems. These are three problems that I would like to focus with this slide. The first one, data is huge. So you might have, let's say, 10 TB of 20 TB of data, right? And it's very likely, or it's probably true that your system does not have 20 TB or 20 TB size. What would you do if you want to, experiment with the data? The only way is to, download this to a 20 TB, a cloud that has 20 TB size, or and then, pick a slice from that data and then try to experiment on top of it. There are different solutions to this problem, but one of the solutions that I found is, Tensor native data storage. So you can fetch a slice from the remote rather than fetching the whole 20 TB and unzipping it and then taking the data that you need. The second problem is storage, versioning, and collaboration, right? So if the data is coming from different sources, and if the data is coming, let's say real time, you're collecting the data, and there is a labeler who is helping you out with labeling the data and storing the data and retraining stuff. There is some way you should be able to version the data, right? What is the version of the data that produced this result, and what happened to this particular slice of the data such that it made an impact on the model performance, right? A negative or positive impact. So you should be able to tell this by looking at this data changes. And if you have multiple labelers, you need a way to collaborate, or you need to enable the collaboration between multiple people who are dealing with the data. So that brings us the question, right? So if you look at this picture on the right-hand side, let's say there is a database that has that's on a commit A, 012, 012, and 012. Then commit B, somebody added a data that has with this. I mean, so with this at the same key, they added a data 012, 222, and 333. Another person added another data with another format. Then how would you merge this? What is the merging? It's not very similar to how we merge things in the source code, right? It's can be combined like this, which is probably insanely blunt thing to do, right? That's not how data work. So you need a way to smartly identify the conflicts and either resolve it or tell the user that what's happening. There's the third problem is the inherent issues that are associated with file-based storage. I'm going to take an example of DBC. I'm not saying DBC is bad. DBC is good in a lot of different things, but this one problem of DBC is probably a problem with all the file-based data stores. So let's say DBC store all your data in DBC cache. Then let's say you have a main.py that you use to train your stuff. Then you actually have a data folder. So that data folder is where you put your data, and DBC cache is where DBC stores the data with the commit information associated to it. So let's say you put 10 TB of data into your data folder. Then you start training. Then after a week, you got another 10 TB of data. You put that again in this data folder. You made the second commit. So your previous commit had 10 TB, and your second commit has another 10 TB, so total 20 TB. Now, if you want to experiment with the slices, when you move to your previous commit, what DBC need to do to present, so you're moving from the 20 TB state to 10 TB state, right? What DBC need to do is delete that 10 TB from this data folder, so you only have the first 10 TB available. Or similar, if you're moving from the first commit to second commit, now DBC need to copy the second 10 TB from the cache to this data folder. And if you're a person who moves between those commits and try to understand what is happening, and if you need to do checkouts between multiple commits in the data a lot, this is going to be a really big problem, right? So this is one of the problems that are associated with file-based store. There are other problems. For example, if you're dealing with the DICOM data comes with a really complicated, sophisticated metadata, right? So your data scientists need to have this super expertise domain knowledge or understanding of how the data is being described in that metadata file. And there is no standard, right? People could define that metadata in a different way. So the solution to this, as I see it, is tensor native data solution. TileDB being the most popular tensor native data versioning solution. You convert all your data to tensors. So the idea is whatever your data is, that it be a sound sample, an image, text, whatever your data is, you're always going to convert this to tensors before you feed this to your model or the algorithm, right? The question is, why not then store data as in the tensor form, right? Then you won't have this problem of you don't need to have the problem of handling with huge data in size, moving between commits, or the file formats, domain-specific knowledge, etc., because the data is in tensor form. So one of the tools that I have built along with the folks at TensorWorks is Hangar. So Hangar is also trying to address this problem in a specific way. So I'm going to quickly run through the way Hangar organizes things in the next 1 or 2 minutes. So let's say you have a remote where you store the data. You do a Hangar clone. Hangar doesn't clone the whole data. Let's say you have 20 TB here. Hangar doesn't clone the 20 TB. Hangar only clone the metadata associated with that 20 TB. So this metadata would tell the Hangar client in your machine that what the data looks like. It's essentially a content hash of each piece in your data, right? So the metadata would be about 80, 90 MB for 10 TB. That's the comparison that we have identified. So your local machine only get 90 MB of data. Then if you need, let's say, 1 GB from that 20 TB, you can do a partial clone. So you get 1 TB from that. 10 GB from that, then you would be able to add more data to it. Even though you don't have the whole data in your local machine, you can still be able to add more data, delete data, essentially, interact with the data in any way that you want without polluting the namespace, without polluting the versioning system. You can push it back, remote accept it if there are no issues. You can fetch the data back again, and you get this data back. So this is how Hangar deals with the data. But like I said, there are other Tensor native data storage solutions. Different solutions address this problem in different way. Do we have questions about data? Okay, all right. Moving on to artifact store. So in the picture, in diagram, if you remember, the thing on the right-hand side, the training and then storing in artifact.
So, sorry, I have a very quick question. I think there's somebody on the chat also. Is the transformation from the original data format, whatever format it is, to tensors always straightforward, or somebody needs to build a dedicated pipeline for every use case? So if it is images, maybe it seems straightforward, but if it is text or tables, is it more complex?
Right. So different solutions, like DialDB has a different solution. Hangar has a different solution. So I can speak from the Hangar experience that I have had. So what we did in Hangar was to build a bunch of utilities to help you with the common formats, right? Text, image. So for text, answering a specific question, for text, what we do is convert it to indices. So then user can, convert it to, use it in the transformers or convert that to word vectors, whatever they want. Then we keep a metadata that maps from the indices to the actual word. So this is what we did with Hangar for text. And we have made a bunch of plugins for audio, text, and then image, a bunch of common formats. And we also made a plugin system where user can define how to read the data. So you can define a function that at a time, so it's similar to Torch data loaders, right? At a time, you can load a file and return a tensor. Similar to that, you can load a tensor and return a file. So you can define this two function and plug it into Hangar, and Hangar will use that when you do Hangar import data from a folder full of data, in the native format. Hangar uses function and to store the stuff too. You don't have to worry about any of this Hangar specific. Only these two functions that can load a file to tensor or convert tensor back to a file. Does that answer the question?
Yes, thanks. And there's another question by Kshitij. How are merge conflicts managed by Hangar?
Right, so Hangar manages this in the most naive way, right? Which I think is more than enough at this stage. The naive way is Hangar always associate a key with the data. So it's similar to if you are talking about file-based data storage, it's similar to the path or the name of the file in the disk plus the actual data, right? So the same map. So Hangar always associate a name with each data point. So the way Hangar manages the conflict is, if let's say image 1 is the name and two people added 2 images to image 1, then that's a conflict. We don't really, so we only check if the data associated with the key is changed. If it's changed, that's a conflict. We don't really, it doesn't make sense to get into the details and try to somehow merge two different data points together. It does not make sense. One correction. It's not Hangar. It's Hangar. H-A-N-G-R. Like the.
Sorry.
No problem. Great.
Okay.
Okay. Moving on to artifact store. So there are a bunch of artifact store that exist right now. MLflow is probably being the most popular. DVC. So DVC initially tried to portray themselves as data store, but I like, for the obvious reasons that I mentioned in the previous slide, I don't really go with DVC for data store, but DVC is good for experiment store and artifact store.
If I can interrupt, I think Kshitij has a follow-up. I'll just give him the mic.
Okay.
Hey, am I audible?
Yes.
Yeah, great. So my confusion still lies around the merge conflict. So in Git, like when there's a conflict, both guys can see the conflict and both of them can actually push the conflict, merge it and then push it. So here, like if, how do they see the data again? Because one guy has put in maybe an image, another guy has put in another image. So do they fetch both the data and there's some possibility to visualize it, or because tensors directly won't make sense to see the data, right?
Agreed. So yeah, so the way it works right now is so when you pull the data, like I said, you only get the metadata, which is similar to the same structure, the key, but instead of the data, a hash, right? So just the hash. Now, the way we look at this conflict is it's easy because it's just, like if you consider this as one line in your source code, key and the value, the hash, we can easily identify the conflict with the same Git logic, right? Because one line has changed by both person, the same line. Now there's a conflict. Now answering your question, tensors by themselves doesn't make sense. Visualizing each of these tensors independently is possible right now. So we have made a Hangar UI where you can, check out to one person's commit and visualize one data piece, check out to another commit and see another person's commit. But I think the ideal way to do is, if there is a conflict, click on a button and show both data left and right hand side. Which is not really something that we have implemented in Hangar yet, but definitely probably the way to go.
Yeah, because even that I would assume require a plugin because not everyone's data would be seen. So makes sense. Sure.
Yeah. So that's how we display the data right now. So similar to how the data is being loaded from the disk to Hangar, there are plugins to visualize common data formats like image, text, audio, etc. But if your data is very specific, like DICOM, similar to the functions that you write for loading and deserializing the data, you would need to write a plugin that visualize the data.
Right. So I guess so. You sort of have the solution if you have a plugin already to visualize the data. Once you have conflict on the same keys, you can just visualize. So essentially the person has the mean code in place, I guess. So yeah, I guess that resolves my question. Yeah.
Right.
Thanks.
Right. Yep. Thank you. Thank you for the question. I have another question.
Sorry. Yeah, there's. Please. You can see the question. Then
yes.
Hangar work for large text visual.
Right. Yeah. So that's I wouldn't call it a GUI because the GUI is in super naive form right now. But the idea is to, in an ideal world, that's how it should be, right? So you have a GUI where you can pick, or you have a command line interface where you can pick the format, and then Hangar does the job. Right now, what happens is you can do Hangar import and give a folder path. Hangar looks at that folder path and try to predict the data format by looking at the extension, which is not probably the error-free way to do it, but that's the most easiest and most reliable way that we could find. So if the format is something that Hangar already understand, or Hangar's plugin system already understand, then Hangar would try to load it automatically. But if it's not understood by Hangar automatically, then Hangar would tell you, I don't have the plugin to load the data. You need this plugin, and you do a documentation. So that's how it is right now. Does that answer your question, Samveed? Perfect. Okay, so yeah. I'll move on, but feel free to ask question and I'll stop in between. So the next problem. So like I said, MLflow is probably the most popular solution here. We have made something on top of Hangar that we think MLflow cannot solve. I mean, obviously because of the certain problems associated with file-based data. So Stockroom is essentially a version control system for your data plus experiment plus model. But Stockroom is one way of doing it. MLflow has another way of doing it, and MLflow has a much reliable and stable API. DBC also does in a very different way. So 3 approaches. I'm going to introduce you to the Stockroom way of doing it. But all of these different products has one or the other approach to essentially achieve the same result. So Stockroom introduces 3 shelves to you: a data shelf, a model shelf, and an experiment shelf. And all of this being tracked. So the stage where you are at right now is being tracked in the Head.Stock file. So this stock file is being tracked in Git. So essentially, if you're using Stockroom, then apart from adding data, you don't really need to worry about checking out the files or checking out the data. All of this is being handled by the Git checkout automatically. So when you do a Git checkout from one commit to another commit, the Head.Stock file would have the commit of the Stockroom, the state of the Stockroom where Stockroom is right now. So the code that you have written would automatically pulling the data at that point in time instead of the latest. So as a data scientist, you don't need to worry about having another toolkit in your kit. You only need to know Git for handling Stockroom. Well, MLflow handles things in a different way. So MLflow put so when we made Stockroom, this was one of the decisions that we needed to make, right? Where to handle this commit. So we handle the commit information in the Git itself, but MLflow handles the Git information in MLflow itself. So you essentially only need to know MLflow to move between commits or handle the checkouts and stuff. DBC, again, is completely relying on Git. There are a few commands that you need to know about DBC, but it's mostly Git. Right. So the problem with artifact store that we're trying to do is trying to handle is at any stage. So this is very much related to the explainability or reproducibility that I've explained before, right? Some of your users raised a question, and you have a system or you have a model that's running in the production. You would need to go back to the same source code, the same time in the source code, model, data. You need to understand what data that model was trained on, what is the version of that model, what is the state of the source code. And you should be able to reproduce the exact same result for the same data piece. So this is the particular problem that we are trying to solve with this artifact store. It has to be versioned. It has to have different pieces. The model, experiment information, your metrics, etc., being stored so that you can look at that and reproduce these things later. That's all with artifact store. Do we have questions? Okay, so I'm moving on, but feel free to. Okay, so here I'm introducing a concept. Oh, no, I'm not introducing a concept. I'm going to move to the next topic, but monitoring and testing is common to the training and serving. So I would like to ask questions to you. What are the problems? How have you faced problems while monitoring your training system? Can you pinpoint me to some of the problems? I don't want to take a lot of time here, but it could be any problem, right? The problem with SSL certificates, right? So very basic infrastructure problems, or you don't know how to connect between 2 machines, or you had issues connecting between 2 machines when you train, or one of your machine went down, right? While training, you had 5 nodes, one of your node went down. So those are infrastructure problems. Then you have problems in the training system. Your the loss is not converging. There are other problems with your model training itself. Okay, so yeah, so I'm gonna display a bunch of issues that that I have copied from David Arnold's talk. So he posted a question in Twitter asking the same question, and these are some of the replies that he has got. Yeah. So yeah, that's of course. Yeah. Thanks for telling us. So there are a bunch of such problems, right? So you need a monitoring system that look at your training infrastructure and telling you that, dude, there's something wrong. Okay, so I'll take this question once I finish this. Otherwise, I'll have to repeat this. Okay, thank you. So these problems, we need to identify this problem, and we need to have a reliable monitoring system that can look at this broad spectrum of issues, right? This issue is not just one issue, two issue. There are hundreds of, if not thousands, of such issues associated with infrastructure and your training system that you need to know as early as possible. So yeah, having that monitoring system, testing system in place is essential for your MLOps system. Okay, so with that, I'm done with the training system. We are moving to serving. But before that, I'll like to take the question from Survey. How do we use a particular version of data from Hangar with a particular model from Stockroom so that we can create a new model? Okay, so the confusion, I'm apologizing for making it confusing. The idea is, if you're using Stockroom, you don't need to use Hangar separately. Stockroom handles data, model, and experiments automatically for you, right? So, the syntax for saving data in Stockroom is exactly the same as syntax for saving data in Hangar, but Stockroom tried to simplify the UI to a bit so that you don't have to know some of the details that you need to know when you're using Hangar. But the idea is Stockroom handles all of this from another level, from an upper level, so you don't have to know about the existence of Hangar at all. Right, so stockroom.page is the website where you can go and look at the doc. But Stockroom is like pre-alpha, so it's bound to have issues. There is another branch that works really well, but it's in an early stage.
So if I may ask a question, it seems that if you want to refer to a previous version of data or a previous version of model,
right,
you need a naming system, right? You need a reference to the previous thing.
Right.
If the reference is a hash, then so I think this might be a general problem. I don't know. You can always refer to any version by a hash, but it's not human readable. It's not. How does a human being remember that I have that?
I mean, this is a problem associated with the Git itself, right? So the way Git solves is by having tags. So when you release something, you git tag something.
Okay.
So that since we are relying on Git, or since the UI, the interface is Git itself, that essentially that you need to do. So whenever you make major releases, you tag the system and let Git handle it.
You might have to go back and look at the commit messages and then decide that, okay, this was very important, so let me tag it so that I can come back to it later.
I mean, yeah, the ideal way to do is not going back while you're moving forward. You tag and move forward. But yeah, I mean, I know it's probably not practically happening all the time. But yeah, that's probably a really compelling reason to build some naming system in Stockroom. Yeah, so yeah, I'll take that feedback and go back.
Is there any other way? Has any other software, what should we call it? Has any other platform built a good naming system around it?
Well, I mean, MLflow has, I think, a pretty good system. I mean, it's pretty good because you have a UI, right? So you go to the UI, and so in MLflow you don't make commits. You don't have to make commits as always. I mean, because the Git and MLflow is different. The Git commit does not pollute your naming system. So you make your data specific or model specific commits to MLflow only when you save an experiment and you know what experiment you address an experiment with the experiment number or something, so that you know how to go back. So yeah, different people handles this problem differently. Yeah, that's another way of solving it. Yeah.
Okay, thanks.
Great. Okay, so moving to serving. Yeah. So in serving, going back to the same diagram that we have had, I'm trying to address monitoring and the serving piece itself. The hardware problems, in my opinion, is common for serving and training infrastructure, so I'm not going to cover that again. So we're specifically going to focus on serving system and monitoring system here. So before going into the problems associated with serving, I would like to quickly introduce the existing serving strategies. So if you have a different serving strategy than I have pointed here, let me know in the comments. So people, like if you don't have a scalability requirement, you put your code behind a Flask server or right now Fast API server, and it would work to a great extent. Execution so things like say SageMaker, you put your model there and let SageMaker handle the problems, other problems with scaling and stuff. Or you have runtimes like TensorFlow serving, Triton, Clipper, TensorRT inference server, MX model service doesn't exist anymore. It's Torch serve now, so that's there. Or you make your own solution, make your own server in C++ or something. Or you take that first approach and Kubernetes everything, right? You put your code in a Kubernetes cluster and then scale it up with the Kubernetes scaling opportunities, right? So these are the current strategies. Serving at scale has few problems that I'm going to describe here. Deploying a model with Fast API Flask is easy, but does it scale? It's not just about the request per second. In a normal request per second that we used to worry about when we deploy normal software, right now it's a bit more complicated because in a normal software setup, the SLA, the request serving time, is probably 10 millisecond, 50 millisecond, 100 millisecond. But when it's come to really complicated model, your model prediction could take 3 seconds, 4 seconds, maybe even 10 seconds, right? And if you're running on CPU, that's a completely different story. So the computation itself is costly, so that you have to compensate with that in some other way. You need to manage the scale, not just the request per second, but the push from the other side, the computation side as well, right? So does it scale? A typical Fast API server, it won't, right? Unless you put that in, like I said, Kubernetes, and put that into an autoscaler and let the autoscaler handles the scale, it doesn't. And even if you're doing that with autoscaler, you end up paying a lot because you are able to scale horizontally, but you are still not solving the problem of reducing the latency. The second problem, that brings us to the second problem, which is you need to run it real time with low latency. Something like, let's say, a self-driving car like Tesla. If your system is making a prediction of when to turn your steering in 10 seconds, then you know what happens, right? So that's not what we need. Other problem is you might have multiple models. Multiple models as in so multiple models could be of different types, right? One is your model, your system needs to make different predictions. So you have different models for making different predictions for one single request from the user. So when your boundary hits a request, you need to give that to different containers that shows different models and collect the result back, collate it, and return back. So that's one problem. Another problem is you would have multiple models for the same problem for doing A/B testing or canary implementation. You have like 10% of the people serving with one model and 90% of the people serving with another model. That's another implementation. There's a third approach to it. There's a third problem with the multiple models, which is you would have a one model that's serving the user, and then you have a shallow model that you keep for monitoring and stuff, right? So having multiple models in production is really hard to manage. And especially, so let's say you have 100 models, and each of this model is being using a canary or exponential deployment. Then each of model will have a bunch of Yeah, thank you, Kshitij, for being here. Yeah, so yeah, multiple models. That's another problem. Another major problem that I face when I talk to big data science team is different people have different preference. So they would be using different frameworks. So the MLOps team, the DevOps team, need to have some solution to deploy, a model built in TensorFlow and a model built in PyTorch, and probably it's likely that this models needs to communicate in a single request itself. So it's hard. CPU or GPU. So it's very likely that your production system would be running the models on CPU, but can you auto batch? If you have like thousands of requests, maybe you can auto batch, and if you're auto batching, then you might need to run things on GPU. Fault tolerance, your things would scale, and let's say your master node goes down, or if you have only one node that goes down, how you handle fault tolerance. So these are the major problems that you face when you serve things at scale. So there are some solutions: Seldon, KF serving, RedisAI. RedisAI is something that I am working on. So I'm going to talk about that a little bit, trying to showcase how RedisAI handles some of the problems. But you have other solutions. I deliberately did not put solutions like TF serving or torch serve because those negate with this point, right? You can only solve for one framework. All right, so moving forward, feel free to ask questions. So this is a statistics that I've taken from one of the RedisAI blog. So RedisAI's performance, so inference time, 0.12 seconds, while a common HTTP server, something like Flask, would take about 0.91 seconds. So that's a difference, right? It's almost like 8 times, 8x different than a common HTTP Flask server. The major reason would be the Flask would be running in a Python context, while RedisAI run things in C context. So that's a major performance gain. Similar to that, you have TensorFlow serving and torch serve. Right now, torch serve is not at all, not even comparable, but TensorFlow serving is doing really well. Plus, there are other products like Triton, etc. So I have a disclaimer here. This statistics, this benchmark, you should not trust this for all the use case. So this is a case which is optimized for RedisAI, and that's why you see RedisAI has the best performance there. But there are probably cases where TensorFlow serving works better than RedisAI, where it is optimized for TF serving. So the case here is that Redis can cache the data. So data locality, a typical example would be if you are building a dialogue system, a chat system. You send your first dialogue, you let your model make the prediction. So along with the prediction, the model spit out a hidden tensor as well, right? The hidden vectors. You need to save those hidden vectors somewhere. Normally what people do is you save those hidden vectors, you convert this to a binary string and save those in Redis in your cache. Not RedisAI, in your Redis, or in a memcache or some cache, right? Because you need to associate that context vector with the context itself. So two people are chatting, you don't want to share that hidden vectors among those two people. Each person has his own context vector. So you need to cache it reliably. So doing that, so that's the first picture. So in TF serving or torch serve or a unicorn serving system, having that data locality in another machine like Redis would affect your performance quite well. But in RedisAI, since you can cache in the local memory itself, that is much faster, which is the performance, which is the reason why you have performance gain, so much performance gain here. But still, the idea is RedisAI is, so what I really want to compare here is RedisAI or TensorFlow serving to common HTTP server, right? The high performance optimized serving system comparing to a naive HTTP server. This is the architecture of RedisAI. I don't think I need to get into it, but the idea is it's multi-framework. You can put any of those framework here. Multi-device, you can put CPU, GPU, etc. You pass the tensors, you make the prediction, you get the tensors back. RedisAI gives free fault tolerance. So in this picture, this is your master. if the master goes down, RedisAI automatically elects another machine as your master, so you don't have to worry about your system scalability, your system going down, etc. And all of this is free, right? You don't have to be a DevOps expert to set this up. Redis comes with all this feature by itself. You deploy 3 machines in RedisAI or 4 machines in RedisAI, and you have this feature for free. Awesome. We're moving to the monitoring in production. So we already covered monitoring in the training system. Now we're going to talk about monitoring in production system. So auditability and explainability, we have covered this to an extent. If your user raises a question about the model's prediction, you need some way to audit that prediction and explain it to avoid legal problems that's going to come in your way, right? So having auditability and explainability in your prediction system is hard because you need to connect some components to your system that can look at the prediction or put you back to that commit, that particular stage where which piece of data that let your model train in such a way that it made this decision, right? You always need to go back to that particular time travel back to that stage. Performance monitoring. So performance monitoring of a model in production has multiple dimensions to it. One of the major component is data drift, right? So for introducing data drift, I'm going to use a typical example. So let's say I've trained a model to make a prediction about what color is my duck, right? So if you train your network with the data set of a lot of yellow ducks and a skewed, set of blue ducks, then even if this is a typical ML problem, right? Even if the model makes the prediction as yellow duck all the time, it's going to be pretty good. It's going to have pretty good accuracy, right? So let's say your distribution shift changes when you move this to production. You start seeing more blue ducks. So now your model has a problem. So similar to that, there's concept drift. Then there are other problems like, let's say you introduce, your system has 2 types of genders, right? Male and female. Now, immediately after you figure out you're going to have people who does not prefer to say the gender or other gender categories, you're introducing other gender types to your gender categories to your application. But if your model is trained only with 0 and 1, or like some categories, the categorical variable gender as just 2 variables, then your model is going to have problems making right predictions. So you need to have test cases running in production where you clearly set your expectation about the model. The gender is in the range 0 and 1. Or the distribution is going to look like this. So if you set this expectation, a good tool to analyze this is What If tool from Tensorflow guys. So it's really good to tell you this kind of distribution in the data and stuff. But there are hundreds of other tools. Hundreds would be exaggeration. Tens of other tools, right? Author.ai is another good tool that let you tell this information. The third point is A/B testing and having shallow models, right? So you need to have this A/B testing setup where you can stream the request to different models, the same request to different models, and have some piece of model making prediction for some set of users, etc., like canary deployment, and shallow models, which is also something I've explained before. So having this kind of setup in the live environment, again, it's really hard. There are tools that helps you do this, but this is a problem, a typical MLOps problem that we need to solve so that we can help the data science. Right? So with that, I am done with the talk. I've covered all the components to it. So if you have more questions, we can talk.
Thank you, Sherin, for such an awesome talk covering so many aspects of MLOps. There are plenty of details, and I guess one could go into each of these sections independently as a talk.
Right, exactly.
There's one.
What if?
Yeah, so I think What If tool released a year back or maybe 2 years now.
Yeah, I think more than 1 year.
So handling data drift is, do people build specific, use case specific tools for that, or there are generic? What if does work in all scenarios? Or
As far as I know, I don't think What If would work in real time with, you can connect it to production machine easily enough. I'm not sure. I haven't tried, but my experience is that you can run it offline, unless you are in a GCP setup where you have it hosted there. I could be wrong there. But yeah, different production serving system try to build different, their own tools around it. Like Converge.io, they have their own set of tools. All the hosted platforms try to make their own tools. And I think there are other independent tools that does this for you. So you connect your data to this tool directly, the real-time data. So you pass your whole training data, and then all the real-time data go through this tool. So they make this production and let you know. But this is, in my experience, it is an immature field. It's still evolving. There are much more things to do. Like there are people who try to do active learning. Like an active labeler who sits somewhere, so data goes to him. The feedback comes, or feedback from the user, like when you click on a button, or when you put the ad, the user clicked on that or not. The feedback. So all of this connected directly back to your learning loop as an active learning setup. So all of this is still in a development field. There are attempts, there are good tools, but I don't think it's mature yet. Yeah.
Any other questions? Does anybody have any other questions?
Great.
Okay. Thank you. Yeah, go ahead.
No. I was just saying my username is just a second. So if you have questions, reach out to me. Send me a DM in Twitter or LinkedIn, and I can still answer your questions.
Okay, thanks a lot, Sherin, for giving this wonderful talk and taking all the questions from the audience. And I hope the audience enjoyed learning it's a pretty vast topic, and
right.
The overview was very beneficial.
Yeah, okay. I hope everyone has got something back from the talk. And thank you so much for having me again.
Thanks, Sherin. Thanks, everybody. Okay.
Yeah.
I'll be closing this session. Yeah. Thank you. Bye.